All right, hi everybody. Can everyone hear me okay? Sweet. Hey, I'm Eben. This is my first Strange Loop. It's amazing. Why are we talking about scheduling? Well, if you read serious documentation by serious people building high-performance systems, you can find a variety of statements along these lines suggesting, vaguely disquietingly, that scheduling overhead can negatively impact the performance of highly concurrent programs. So you can find this in Nginx, you can find this in the MySQL docs, and you can find statements to the effect that thread context switching is somehow intrinsically expensive. But these statements are not quantified or justified in this documentation, which is fine, because that's not their job. But as a performance engineer, this makes me kind of uneasy. So scheduling, which for the purposes of this talk means multiplexing a lot of tasks onto few cores, few processors, a priori is kind of a black box. Like, you can write a lot of concurrent code without needing to worry deeply about the internals of the Linux kernel scheduler or the runtime scheduler if you are using a language that has its own concurrency primitives. So it's this black box, and the claim is that it can potentially negatively affect our program's performance. So this is not good. I don't like black boxes that make things slower in mysterious ways. So there's a pretty natural set of questions that we can ask about this scheduling business. So how expensive is a context switch intrinsically? When the Go language authors say it's slow, what do they mean? Can we measure it, or do we just have to take their word that it's slow? And how does the Linux kernel scheduler work anyways? When you switch from one Chrome tab to the next, or spawn a new thread, what's going on under the hood? And what about user space schedulers? So languages like Go and Erlang and Haskell have their own concurrency primitives that are sort of like operating system threads, but not actually operating system threads. So those are scheduled by the language runtime. How does that work? Is it somehow fundamentally different? Are there common design patterns that all these scheduler implementations follow? And do they make different trade-offs? Do they target different performance use cases? And how do they do so? So that's what I'd like to explore in this talk, by doing a few pretty basic experiments and a little bit of experimentation and source diving. So to start off, let's talk about scheduling in kernel space. I'd like to start this discussion by talking about how we can actually estimate kernel context switch cost. So you have a processor, it runs Linux. I'm only going to talk about Linux in this presentation, sorry. But if you're initially running task A on a core, like a Chrome tab, and then you switch to task B, which is something else, I don't know, syslog, whatever, there's some intrinsic cost to that operation. And measuring the duration of a context switch is probably the first heuristic we can establish for how much concurrency can our system support. If a context switch takes 10 microseconds, we'll never be able to run more than 100,000 threads on a core because we will spend all of our time context switching. So maybe it's okay if context switching accounts for some reasonably significant part of our effective workload in highly concurrent scenarios, but it's probably not okay if that's all that we're doing. So there's a classical approach to estimating the intrinsic direct cost of a context switch. It's playing ping pong. We'll set up a scenario where we do a bunch of context switches and as little other work as we can. So for example, you start a thread, thread A. You start a thread, thread B. You connect them with two pipes. And then you have thread A write to thread B over one pipe. Thread B will wait and read it, then write back over the other pipe. Thread A will wait, and so on. So what has to happen is that you end up switching back and forth between these threads effectively as quickly as the operating system can do it. Make sense? So in C, the implementation of such a worker thread might look something like this. Now, I can't really write C. I try. It doesn't work. Fortunately, I don't have to. This is actually a built-in benchmark in the Linux kernel source tree. You can run it with perf bench sched pipe. And you can pass -t to say two threads, not two processes. It doesn't really matter. So you can try that out on my laptop. It takes about 4.5 seconds to do 1 million pipe operations. What does that mean? So it tells us 4.49 microseconds per operation. And that gives us an upper bound on the direct cost of a thread context switch. that upper bound is actually 2.25 microseconds, because what the authors of this benchmark are calling an op is a read and then a write. So there are two context switches. If you think about it, it makes sense, I promise. Cool, so that's a pretty good heuristic. Is that our final answer? No. So you can't actually trust a benchmark if you just run it and don't undertake at least some minimal effort to analyze it while it's running. There will be no more bad poetry in this talk, I promise. But there's a serious point here, which is that we're running a bunch, sorry.
So for the 2 microseconds, how many instructions roughly is that processor?
Oh, I have no idea. It's a 2 gigahertz processor. You can do the math. Great. So, sorry, the question was how many instructions does that correspond to? And it's 2 microseconds divided by 2 gigahertz. I don't know, a bunch. So, benchmarking, right. So we have this benchmark that's doing thread ping pong, and we have a mental model of what it's doing. It's running thread A and then executing a context switch, and then running thread B and then running thread A. So how well does this map to reality? Well, we can find out with a tool called perf_sched. What's perf_sched? It's another perf subcommand. Perf has a lot of subcommands. What perf_sched does is it records scheduler events and then can show you an output, a timeline of context switches, wake-up latency, etc. Seems like something that might be applicable to a discussion about scheduling. So you run perf_sched record over our benchmark and get basically a dump of everything that happened in the scheduler while we were running this. This is really dense. But we can highlight one thing. We're switching from something called sched_pipe, okay, that sounds good, to something called the swapper. What's the swapper? It's basically what the kernel runs when idling. So that doesn't really map to this mental model very well. What's going on? So I ran this on my laptop. My laptop is recently modern. It has multiple cores. The scheduler sees thread A is doing a bunch of work. Thread B is doing a bunch of work. OK, I'm going to put thread A on this one core and thread B over on this other core. But that introduces a net slowdown into this benchmark, because every single write to a pipe and then read from it introduces a cross-core wake-up. And it turns out that that actually adds some overhead to this benchmark. And partly because waking up from the idle state is a little bit more expensive than a direct context switch, and partly because the cross-core communication degrades cache performance. So let's run the benchmark slightly differently. I pin all the tests to core 0. It's twice as fast. All right, active benchmarking. So we didn't just go with the first result we saw. We used a tool to analyze the internals of the benchmark, verified that we were running a benchmark which actually corresponded reasonably well to our mental model of what it is doing. And now we have a more plausible number. So we've learned something. The direct cost of a thread context switch is around 1 microsecond on this machine with lots of caveats. Sorry, you have a question?
I want to check some terminology.
Yes.
You're saying thread, it looks like you're talking process context switch versus in-process thread switch.
These are 2 threads in the same process. Numbers are slightly different. In this benchmark, if you switch between 2 processes and 2 threads, the question was about whether this is a thread context switch or a process context switch. In this talk, we will mostly be talking about thread context switches in a highly multi-threaded single process program. From the perspective of the Linux kernel, there's not that much difference. There are slight variations in the numbers that you get. Does that make sense? Cool. So you ran perf_bench pipe -t. That -t meant run 2 threads, not run 2 processes, but they get different PIDs. So we have a number, and we have some meta lessons. Benchmarking is tricky. We can't just run random experiments. We need some level of introspection into the scheduler. And for that, it's helpful to have some idea of how the scheduler actually works. So let's talk about the internals of the Linux kernel scheduler. So you know a priori it has to do two things. It has to preempt misbehaving tasks, and it has to prioritize important tasks. All right, we can do this. I still can't write C, but we'll try. So we'll keep a list of running tasks, and whenever we want to schedule, we'll iterate through that list, pick the task with the lowest countdown to run next, and then for each other runnable task we'll decrement the countdown, counting down higher priority tasks faster. So over several iterations, high priority tasks will effectively move to the front of the line. Then, if there's a next task that we should switch to, we'll switch to it. This is actually how the Linux kernel scheduler worked in 1995. All right, it was 75 lines of code, not 15. I cut out some stuff about timers. But still, not that complicated. Today, it's a lot gnarlier. In addition to preemption and prioritization, the Linux kernel is expected to support a notion of fairness. It's expected to scale to multi-core machines. It should be power efficient. It should support resource constraints like C groups, so you can run your fancy pants Docker containers or whatever, and so on and so forth. And as a result, it's a lot bigger. But there are a few salient design principles that we can highlight in the current implementation of the Linux kernel scheduler. It's called the completely fair scheduler. There are other scheduling policies in the kernel, like real-time and FIFO. We're not going to talk about those. This is the default, probably what's happening if you're running a concurrent program in the Linux kernel. So in general, scheduling happens on a per-core basis. And we'll talk about inter-CPU load balancing later. Why is this? It's because a single global data structure that's frequently read and updated tends to introduce contention and severely degrade cache performance. So this allows the kernel scheduler to scale well to 64, 128 core machines. Now, on each core, we maintain a run queue of runnable tasks, which isn't actually a queue, or it's sort of a queue. It's a red-black tree that's ordered by task v runtime. What v runtime is virtual runtime, which is effectively real task runtime divided by task weight. So high priority tasks have their v runtime scaled down. As tasks run, they accumulate v runtime. Whenever it's time to execute a task switch, the scheduler simply pulls the leftmost task off the run queue and runs it next. Concurrently, preempted or new or woken tasks go onto the run queue before they can be rescheduled. So the run queue is effectively a timeline of future task execution, and tasks are guaranteed a fair allocation of runtime. What do I mean by that? Okay, so if you look at this line here, the middle line, we ran task A, which started out with a low v runtime, then switched back to task C. But we can see that task A still has lower v runtime than task E, so it will run before task E. And what this means is that over time, each task gets a fair share of processor time, which is not true if you apply a simple scheduling policy like FIFO or LIFO, where you just round robin through all the tasks. So it's reasonable to ask what actually prompts a task switch. Two things, pretty much. The running task blocks and explicitly calls into the scheduler, hey, I'm going to have to wait for something. Kernel, you can schedule me off and run something else. Or the running task is forcibly preempted because it exhausted its scheduling quantum. This is sort of an intricate and cool dance. I'd like to talk a little bit about how preemption works. Unsurprisingly, it's driven by a hardware timer. Every so many milliseconds, timer goes off, interrupt handler. Interrupt handler routes this timer to scheduler code, which checks if it's time to reschedule the current task. Preempting directly from this handler could cause funny stuff to happen if we were in a nested kernel control path where we were already handling some sort of other interrupt. So instead, the interrupt handler, instead of directly switching tasks, sets a flag in the tasks thread info struct, signaling that rescheduling is due to happen. Hey, this flag is set. Then, when it's safe to switch contexts, on the IRQ exit path, we check that flag, and if we need to, we do whatever cleanup work, and then call schedule. Schedule is, unsurprisingly, the core scheduler function. It dequeues the next test to run, enqueues the preempted one, swaps out their processor state, registers and what have you, does whatever cleanup it needs to, and then starts running the next task. A little intricate, generally works. Cool. So, thus far, we have a scheduler that supports preemption, prioritization, and fairness. Let's talk a bit about how it scales to many core systems. So, like I mentioned, per process run queues limit contention and cache thrashing, but they can lead to severely unbalanced task distribution. So in this picture, Core 0 has a bunch of tasks. Core 1 only has one. Core 1 is underutilized. So each core periodically does a simple load balancing procedure. But fair balancing is tricky. Say task C has higher weight, meaning higher priority than tasks A, B, and D. If we just looked at the run queue length, thread core has a bunch of tasks, core 1 only has one, okay, I'm going to move some tasks from core 0 to core 1, then we would unfairly deprive the high priority task of its due runtime. We could try balancing based on total task weight. So, all right, core 0 has each task has weight 10. There are 3 of them. It has weight 30. Core 1 has one really high priority task with weight 100. But if the high priority task frequently sleeps, this ends up being really efficient because core 1 could idle for long periods of time. So instead, the kernel does something really clever. Balancing uses a load metric based on a combination of task weight and CPU utilization to ensure that high priority tasks get their fair share of time, but cores are efficiently utilized even in the presence of processes that frequently sleep, wake up, sleep, wake up. So at this point, you might be thinking, this is kind of complicated. I have more questions. How am I going to answer them? Like, what about the power efficiency stuff that you talked about and aren't actually going to dive into in this talk? So you could listen to some bozo blather on and believe what he says. You could stare really hard at the source code and try and figure it out. Or, and I recommend this approach, use ftrace, the function tracer. This is the coolest thing. How many people here have heard of ftrace? All right, some. That's cool. So ftrace is this amazing technology. It dynamically traces almost all function entry and return points in the kernel. So when disabled, it has almost zero overhead. You turn it on, it has overhead. Obviously, it has overhead. But you can see a call graph of every single function that the kernel is calling. That's amazing. It's a Linux tool. It's kind of gnarly to use. You mount this debug file system, and then you cat some stuff to it. But you can read about it on the internet. It's not too hard to figure out. And you can answer questions like, what's the code path through the scheduler look like? All right, we call schedule, and then we do a bunch of stuff. Or what happens when you call read on a pipe? Well, you could grep through the source code and try and find pipe read. Or you could just write a little program that reads from a pipe, run ftrace. All right, it's doing some stuff and eventually scheduling. Makes sense. So my recommendation for diving deep into the internals of the Linux kernel schedule, or really the Linux kernel at all, is use ftrace to build a function call graph and figure out what's actually happening on your system. Way easier than trying to do it in your head with the source tree. Pretty cool. So the completely fair scheduler, it's performant, scalable, robust, traceable. End of story? No. Let's switch gears and talk about scheduling in user space. So there are good reasons why some language runtimes don't simply fall back to native operating system threads and instead offer you different concurrency primitives. These are languages like Go, Erlang, Haskell, others. You might want to target different performance characteristics. Let's say you want concurrency constructs in your program and you want 10 million of them. You can't have 10 million threads. We already saw that because a context switch takes 1 microsecond. You'd just be context switching. You might want to decouple concurrency from memory usage. One severe limitation of operating system threads is that stack size is fixed at creation time. And in practice, this tends to be the bottleneck to creating lots and lots of threads before context switching. You have 1 million threads, each one has a megabyte of stack space. All right, you need a terabyte of memory. That's expensive. And you might want to support managed memory runtimes by integrating the scheduler with the garbage collector. We won't really talk about this in this talk, but it is a legitimate use case. This is part of how Go achieves very low latency garbage collection times. So language runtimes implement their own schedulers on top of the operating system baseline. Are these schedulers fundamentally different from the kernel scheduler? Do they share significant design patterns? Let's take a look. I want to look at 2 languages. One is Go, the other is Erlang. So let's talk about Go. In Go, how many people here have programmed in Go? Okay, cool, good number. So in Go, code runs in Go routines, which are sort of like threads, ostensibly more lightweight and managed by the language runtime. They're supposed to be very cheap to create and dispose of. Go routines are multiplexed onto OS threads in a process called M-to-N scheduling. So you have relatively few operating system threads at any point and a whole lot of Go routines. And the language runtime takes care of managing it for you. So the claim is that rescheduling a Go routine is much cheaper than rescheduling a thread. So what do Donovan and Kernighan mean by much cheaper? Does anybody have a guess how we could find out? Yeah, ping pong. So we can do this in Go. Go has a concurrency primitive called a channel that lets you send data between Go routines. It's kind of like a pipe. So this is a crude heuristic. We're not going to deep dive into this benchmark. But we can write a simple Go program that spawns 2 worker threads with channels between them and plays ping pong back and forth. Run it. All right, 0.2 microseconds per switch. That's way faster. They were right. That's not surprising. They're Donovan and Kernighan. So what's the Go scheduler doing? Let's take a look. So in Go, runtime state is basically described by 3 data structures. There's an M, which represents an operating system thread, a G, which represents a Go routine, and a P, which represents general context for executing Go code. Each P contains a queue of runnable Go routines. So far, this is not that different from Linux. You have some data structure per core, and it has a run queue if things are going to run next. And at context switch time, the next Go routine is pulled off the run queue and run. So on an N-core machine, we end up with up to N threads concurrently executing Go code. Still not that different. However, there's no regularly scheduled inter-P run queue load balancing. Instead, Go routines which were preempted or blocked in syscalls go onto a special global run queue, and a P which becomes idle can steal work from another P. All right, these Go routines are mine now. Finally, a separate sysmon thread implements P handoff if an M blocks in a syscall. What do I mean by that? All right, we're running Go code. The Go code is green, and then it executes a syscall. It's going to read a ginormous file from disk, and then it blocks in the syscall. The syscall is yellow. What happens? All the other Go routines that were scheduled to run on that thread are now blocked by this one Go routine. That's no good. So the sysmon thread periodically checks if this bad situation is occurring. If it does, it possibly allocates a new thread with a new M structure, takes the P that was priorly associated to M1, and says, okay, all these Go routines are now going to run on this new thread. Pretty cool. The sysmon thread also checks for long-running Go routines that need to be preempted. Pretty plausible. However, because preemption needs to play nicely with the garbage collector, preemption can only happen at Go function entry. So tight loops, if you just do a for loop forever, can potentially block arbitrarily. This is a bit hazardous. So in Go, context switches are fast by virtue of implementation simplicity and not merely because they're avoiding the round trip into kernel space. This is a design choice. We can support lots of concurrent Go routines, like millions, but we can't assign them priorities. We don't have strong preemption guarantees. And to illustrate the practical effect of this design decision, I'd like to contrast this implementation with Erlang. Erlang is also a language ostensibly designed for highly concurrent programming. In Erlang, concurrency primitives are called processes, but actually have nothing to do with operating systems processes, except for the fact that they do not share memory. Processes communicate exclusively via asynchronous message passing. So unlike Go and C, Erlang code is actually compiled to bytecode and executed by a virtual machine. It's sort of like the JVM or CPython or Ruby. This architecture enables a simple preemption mechanism, which is neither timer-based, like the Linux kernel, nor watcher-based, like Go. It uses the notion of a reduction budget. So every Erlang process, when it is scheduled, gets a reduction count, which by default is about 2,000. And everything you do is going to cost you reductions. Calling a function, decrement the reduction budget. Send a message to another process, same thing. I/O, garbage collection. And once you use up your reduction budget, you get preempted. This is so simple that we can actually see it in code. So the Beam emulator source code, the Erlang virtual machine source code, is in C. The core of the emulator is this gnarly 3,700-line switch statement. It's got hella defines and gotos, but this is what matters. If we want to call a function, the next bytecode instruction is going to say, call a function. So we set the continuation pointer, advance the instruction pointer to point to the next bytecode instruction that we're going to execute, and then call a macro called dispatch. What does dispatch do? It dispatches. If we still have reductions in our budget, we're going to decrement the reduction counter and go through the emulator loop for the next instruction. Go back to the top of the switch statement. But if we're out of reductions, we're going to context switch. So let's take a moment to think through the implications of this design. So we know we have a reduction budget of about 2,000 reductions, and each function call is going to cost us one of those. How long do functions take? Not very long normally. This means we could be calling into the scheduler at sub-millisecond intervals. Scheduling is highly granular. What are the consequences? The maximum throughput of our program is going to be affected. If we just want to do lots and lots of number crunching, it's going to be somewhat slower in Erlang than in a language like Go. But on the other hand, the preemption latency is highly predictable. It doesn't depend on the scheduling of a separate operating system thread or the prompt handling of a timer. Why does this matter? Let's try an experiment. This is a small Go program. First, we're going to spawn a bunch of busy tight loops to saturate all the cores on our machine. I did this on my laptop. My laptop has 4 cores. Then we're going to sleep for some predetermined interval and measure how long we actually slept versus how long we expected to sleep. This is a crude estimate of the effective preemption latency that our program is seeing when the CPU is saturated by work. Does that make sense? So this is not a rigorous benchmark. I mean, obviously, you could raise a lot of objections. Yes, I'm sorry. Thank you. You should do code review for me. Yes, so the jitter is how long you actually slept versus how long you expected to sleep. And if you run it, you get a latency distribution like this. Preemption latency varies from sub-millisecond to up to 40 milliseconds. Let's compare this with an implementation in Erlang. It's actually Elixir. So Elixir is a language that runs on the Erlang VM. Its syntax is more Ruby-like, so it doesn't make my brain hurt. And if you haven't read Erlang, it probably makes sense. So we spawn a bunch of busy tight loops to saturate the cores. We sleep for some targeted amount, and then we measure how long we actually slept for and use the difference between that and our sleep target as an estimate of preemption latency. What does that look like? It looks like this. Nearly consistent sub-millisecond preemption latency. That's the difference. Erlang trades some throughput for highly predictable latency. Go does the opposite. Yes?
Maybe a silly question. Was it significant that in the Go example, the Go routine was calling time.now, which is probably calling get time of day, and in Elixir, it was just bumping a counter?
That's an excellent question. The question was whether it's significant that the Go function was calling time.now and the Elixir function was bumping a counter. You, sir, are an amazing reader of code on slides. Yeah, it's not significant. The reason we're calling time.now in Go is because we need in Go, in our tight loop, we actually need a function. We actually need to execute a function call, because if we just did for, like increment the counter, we wouldn't call the scheduler. We totally deadlock it, like we mentioned. So it's not actually significant. Time.now is like the first thing I thought of, but that's a great point. Thank you for bearing with me through this little exercise. Maybe we've learned something. I certainly did. Scalable scheduling, not that mysterious. All the implementations that we saw share some patterns. They use independent run queues with periodic load balancing to scale well across multiprocessor systems. They preempt at safe points to prevent rogue code from bringing things to a halt, but they make different design decisions. The Linux kernel scheduler gives you a very granular priority system. You can nice your process to all sorts of different things. The Go scheduler is very simple, no priorities at all. And you can trade latency predictability versus baseline overhead. Code in Go in general will run a little bit faster than code in Erlang because you are not paying this fairly constant overhead cost for granular scheduling. But you may suffer greater variance in latency in certain scenarios. And there are other trade-offs, but these are maybe the most salient. That's all I have. Thank you very much. I would love to take questions. Yes?
Can you tell a little bit more about the differences, details of context switching, like native threads and green threads? It's like native threads, like config registers, right? Like say, like some set of registers and recover, like restore some set of registers, like performance machinery. How that's different from the like the Go scheduling does. Or like specifically for context switching.
Right, that's a good question. So the question was, what's the distinction between context switching between native threads and between green threads? So it depends a little bit on the language runtime. So when you, in the Linux kernel, when you switch between threads, you do need to save the registers in some other thread state and switch that out for the next thing you're going to execute. Because Go code compiles to native function calls, the actual mechanics of the context switch are fairly similar. You save the registers of the function you were in, and then switch to the next function. In a VM language like Erlang, like the actual registers on the machine are the registers of the VM and not of your Erlang functions. So that's sort of fundamentally different. But the actual mechanics are like quite intrinsic, and I can't really do justice to them. So I encourage you to use something like ftrace you can sort of pick apart the individual steps of the context switch. But it's like quite hard to justify this quantitatively. But my opinion, and it's only an opinion, is that the register saving is a relatively small part of the overall intrinsic cost of a context switch, and most of it is attributable to the general complexity of the scheduler machinery. That is my opinion, but I don't have, like, don't take that as truth, because I can't really give you a concise way that you could go and prove this for yourself. I mean, a Go context switch still takes 200 microseconds, which is still equivalent to a good chunk of work. Like, yeah, so the question was about cache utilization, which is, in general, something that's quite difficult to analyze convincingly. But my claim is, if your Go routines have a big working set and you switch from Go routine A to Go routine B, like, you're still going to see cache penalties. And if your threads have a big working set and you switch from thread A to thread B, you'll see big cache penalties, like, no matter what the scheduler is doing. But if the working set is small, that is not necessarily the case. Does that make sense? Yes. Cool. Any other questions? In the back there. Mm-hmm. So the question was, the reduction budget is 2,000. If you change that a number, what happens? That's an excellent question. So what I would say to that is two things. So changing the reduction budget changes the granularity, obviously. If you double it, you will see preemption latencies on the order of 2 milliseconds, not 1 millisecond. But it doesn't change the predictability. Part of the reason why there's a lot of variance in Go is because the preemption is driven by a separate operating system thread. So preemption latency is beholden to that operating system thread being scheduled by the operating system. And there's hundreds of milliseconds, not hundreds of milliseconds, but a few milliseconds of latency variance there. So it's absolutely like a sliding spectrum of granularity versus preemption latency. Does that make sense? Yes. Yeah, I'm honestly not entirely sure why Go works like this, but you can call something like sched.yields to explicitly yield. Like, pretty much every runtime has a construct like that that allows you to explicitly yield in that tight loop. Yes?
A couple of questions. First was that comment about Erlang.
Mm-hmm.
If you have a C function, it's called a NIF.
Mm-hmm.
If you load a NIF into Erlang, then the reduction counter doesn't work anymore unless you explicitly call it in a very recent version of Erlang.
Mm-hmm.
So you can run into this situation where you have something on a scheduler and it basically hogs the scheduler until that C call is completed. And that C call, of course, can do arbitrary things, which might make you sad. That's one reason why Erlang programmers like me try to avoid C as much as possible when possible. So that's one. And then two is there's a paper in Eurosys called "The Decade of Wasted Cores."
Mm-hmm.
It talks about the unfairness of the Linux scheduler or the inefficiency of the Linux scheduler. I just wondered if you had an opinion or thoughts about that paper.
Thank you very much. So for posterity's sake, the first comment was that in Erlang, if you basically call into C extensions, the reduction count doesn't go down unless you explicitly decrement it. So it is totally possible still to effectively break the scheduler by calling C. I mean, that sort of makes sense. And the second was about the paper that appeared a few months ago called The Linux Kernel Scheduler, A Decade of Wasted Cores. That paper was the catalyst for me proposing this talk to Strangeloop. Here's what I think about it. I'm not a systems researcher, so maybe I'm not really doing it justice. There are two parts to that paper. One is where they sort of describe the general architecture of the Linux CFS scheduler, especially on multi-core systems, and I think it's a fantastic exposition. As for their claims about wasted cores, it seems to me like the bugs that they found apply to scheduling on NUMA architectures with lots of cores, like 64-core machines. And the like regression cases that they mentioned in that paper were things like running a Ruby web server and also compiling the Linux kernel or something like that. Workloads that I personally couldn't quite identify with real workloads. And I think like the paper is cool, but if it had represented a real improvement, they should have like posted it on the LKML, and like their patches should be in the Linux kernel. As far as I know, like right now, they're not. That could have changed. And like they built some tools to analyze scheduler performance, but I rather would have seen them leverage like more general purpose tools in the kernel infrastructure, like ftrace or perfsched. Because like they built their own, but you need a custom kernel. I don't know, I'm not hating on the authors of that paper, but I think the things that they found were relatively special purpose regressions, and their broader point that it's kind of a gnarly piece of code, like obviously stands. It's like pretty complicated. Does that seem reasonable?
Yeah, thanks. Appreciate it.
Cool. I think we're out of time, but please come talk to me if you care about this at all. Thank you.